Hey everyone, welcome back to the channel. In our last video, we broke down the source transport trap model, a powerful way to understand how gold deposits form. We talked about how gold needs a source to come from, a pathway to travel through, and the right conditions to finally settle and form an ore body. Now that we have got the framework in place, it's time to see how this actually works in the real world. In this video, we'll dive into some Canada's most famous gold deposits, places like Red Lake, Abitibi Belt, Hemlo, and we'll walk through exactly how the STT model applies to each one. If you're not familiar with Canadian gold fields and their mineralization types, be sure to check my other videos in my channel where I give a full overview of the major gold camps across Canada and explain the different deposit types found in each. By the end of this, you will not only recognize how these deposits form, but you will also see how we can use the STT model to explore for new gold deposits. Let's dive into the Red Lake in Ontario. It's an orogenic gold in Greenstone Belt. The Red Lake camp lies in the Archean Red Lake Greenstone Belt in Uchi sub-province in Superior Creighton. It's one of the largest and highest grade gold camps in Canada, and the gold deposits such as Campbell Red Lake Mine are hosted in about 2.99, 2.96 GA tholeiitic basalts of Balmer assemblage, and also is cut by younger porphyry dikes, and these are associated with regional D2 shear zone system as explained in the last video. Talking about its source, gold-bearing fluids were generated during Neo-Archean tectonism and metamorphism during the Kenoran orogeny. The main gold stage at Campbell Red Lake was synchronous with regional metamorphism and platonism, suggesting deep metamorphic fluids as a source, possibly with input from magmatic degassing. Fluid inclusions and gas analysis indicate an unusual water-poor, carbon dioxide-dominated fluids. The figure here from Chi et al. 2006 show the gas composition of fluid inclusions from different quartz generations at Campbell Red Lake. Across all samples, carbon dioxide, you can see, is the dominant with minor methane and nitrogen, and importantly, no detectable water. So Chi et al. Proposed that this could derive from high-grade metamorphism in the lower crust with carbon dioxide enrichment from either mantle influx or partial melting that removed water. And the gold likely was leached out from the greenstone rocks, basalts, iron formation by these carbon dioxide methane fluids. Talking about the transport, the ore fluids were focused along the district's major shear structures, notably the mine train and east-southeast trending D2 shear corridor along the Campbell fault zone, which provided the high permeability pathways from deep crust to the sites of deposition. Fluid flow was probably episodic, driven by seismic pumping. At the deposit scale, the Campbell and Red Lake mines sit adjacent to the folded ultramafic contacts within the shear zone. Structural setting that localized the shear zone, is the structural setting that localized fluid flow into ore chutes. Importantly, fluids remains carbon dioxide rich up to the sites of deposition, implying they stayed in a confined system with minimal mixing with groundwater, and the chemical transport was via gold bisulfide complexes if any water was present. If the fluid was nearly pure carbon dioxide, methane, more exotic transport like gold vapor complexes or H2S gas transport might have occurred. Gold deposition at Red Lake was controlled by both structural and chemical traps. Structurally, as the transpirational shear zones moved, they created dilation sites such as fault hinges, breccia zones. The high-grade zone at Red Lake occurs in brittle stockwork and breccia veins in an antiformal fault hinge, a classic structural trap where dropping pressure in the opening fractures caused gold to precipitate, as we explained earlier. Textures like coliform bands indicate episodic pressure fluctuations. Chemically, gold is associated with arsenopyrite and silicification that overprinted earlier iron carbonate veins. The fluids likely reacted with iron from the earlier carbonate ancrite veins, causing arsenopyrite to form and precipitating gold with sulfide. This replacement style, carbonate to quartz plus arsenopyrite and gold, is evidence of sulfidation trapping. Additionally, Red Lake's carbon dioxide rich fluids may have undergone phase separation, boiling in the sense of unmixing into vapor and liquid carbon dioxide water phases. Actually happened at the site of mineralization. If so, the loss of H2S into vapor phase could also have triggered gold precipitation. In summary, Red Lake's enormous grade and volume resulted from a perfect confluence of STT. A prodigious deep gold source, efficient structural vertical transport, and a trap where structure and chemistry caused rich gold deposition. The fold dilation plus wall rock sulfidation and fluid immiscibility caused this rich gold deposition. Let's move on to Abitibi Greenstone Belt, its giant arcing gold district. This is Superior Province and Abitibi Sub-Province. And this is central and southern Abitibi. The Abitibi is one of the world's most prolific gold-bearing greenstone belt with numerous deposits, Timmins, Kirklands, and others. The belt consists of arcing volcanic assemblages and associated sedimentary basins crisscrossed by large crustal faults. Gold deposits are typically orogenic and forming in quartz carbonate vein system within shear zones, often near contacts of different rock types. Two notable structural corridors are Destor Porcupine Fault Zone and also Lauder Lake Cadillac Fault Zone, each associated with multiple major mines. Talking about the source, gold in Abitibi was sourced from extensive metamorphic devolatilization of greenstone belt from oceanic crust and sediments during Archean orogeny. As the Abitibi underwent regional metamorphism from green schist to lower amphibolite facies and also deformation, huge volumes of water and carbon dioxide fluids were expelled from the rocks, and these fluids scavenged gold plus arsenic and some other elements from the mafic volcanics and iron-rich chemical sediments, such as banded iron formations that occur as interflow units. The metamorphic model is supported by the general lack of temporally associated granitic intrusions with many gold deposits. However, Abitibi is complicated by local magmatism. There are many felsic porphyries and cyanide intrusion that are especially associated with gold zones. This has led to debates about magmatic contribution. For instance, Canadian malartic is a giant low-grade deposit in metasediments, have been alternately interpreted as an oxidized intrusion-related system with a mid-crustal monzodiorite sourcing the fluids. Goldfarb and Pitcairn 2023 argued that even in such cases, the deep crustal metamorphic fluids is more plausible, but the debates illustrate that metamorphic versus magmatic source is an open question for some Abitibi deposits. So in overall, the consensus is that most major Abitibi gold camps are products of supracrustal metamorphic fluids, given the regional scale of mineralization and absence of consistent intrusive timing. The presence of abundant carbon dioxide and low salinity inclusions in vein quartz supports a metamorphic origin. Talking about the transport, the Abitibi's gold-bearing fluids migrated upward through large transcrustal fault zones that were active during mineralization. The Porcupine, Dester, and Cadillac faults, for example, were fundamental conduits, tapping deep fluids reservoir and channeling them into the upper crust. And these shear zones often mark terrain boundaries or major stratigraphic breaks and can be traced for tens or hundreds of kilometers, essentially plumbing lines that fed multiple deposits along their lengths. Within the broader corridors, secondary structures like splays, fault hinges, fault intersections, further focused fluids into specific deposits. In the Timmins Porcupine Gold Camp in the Western Abitibi, mineralization is strongly aligned along the Porcupine Fault Zone, and numerous porphyry intrusions occur along this fault that was debated in explaining the source. Here we can discuss how these porphyry intrusions influenced the transport. McDonald and Pierce in 2018 suggested that these intrusions provided mechanical heterogeneity that local shear strains partitioned around. So fluids traveled up the crustal fault and then into the fractures around these porphyries. And as they describe, gold-bearing fluids and intrusions followed the same crustal structures, and the spatial clustering of the intrusion and ore together is their evidence that the structures were pathways for both magma and hydrothermal fluids. Talking about the trap, the variety of gold deposit style in Abitibi means that all traps varied, but common themes are structural dilation and wall rock reactions. In the Timmins camp, many ore bodies formed at bends or splays of the main fault zone. As you can see here, for example, the Hollinger and McIntyre mines were localized exactly where the Porcupine fault steps or jogs, producing extensional veins. Intrusions at Timmins also helped create traps. As we discussed, the fluid both fractured the intrusions and deposited along intrusion margins. And these porphyries served as structural traps, and gold precipitated in dilatant fractures along the porphyry margins, essentially where the stress shadow around the rigid intrusions allowed open source. Additionally, these intrusions and adjacent rocks were often strongly altered. Sericides, carbonate, sulfide alteration were all developed and indicating sulfidation and wall rock interactions. This altered rock, for example, iron carbonate rich albite sericide zones, this all provided a chemical trap as gold bearing fluid deposited pyrite, arsenopyrite, or others in the wall rock. Similarly, along the Larder Lake Cadillac Fault, in the Kirkland Lake Camp, gold veins are famously associated with albitized and carbonatized ultramafic rocks with felsic cyanides. So the trap there similarly involved structural opening, veins along fracture zones like the main break, and chemical triggers such as the fluid reacting with ultramafic wall rock that cause sulfides with gold to form. In the Malartic area, which has a more disseminated bulk tonnage style deposit, the trap was largely a chemical precipitation in a porous metasedimentary rock, likely by cooling and fluid mixing in a relatively permeable, wacky conglomerate unit. That is a more typical case for the Abitibi, which is why it's been interpreted variously as a deep transported magmatic fluid system. Nonetheless, across the belt, the most consistent trap is structure. Rock structure controls both transport and deposition, meaning that wherever the structure permitted, the fluid deposited the gold. The presence of iron-rich host rocks, such as basalts, banded iron formation, ultramafics, also enhanced deposition through sulfidation. In summary, Abitibi's gold endowment reflects a metallogenic perfect storm. Ample source, big faults for transport, and repeated structural chemical trap sites in an evolving Archean origin. Okay, now let's dive into the Hemlo deposit. It's located in Ontario, the unique metamorphosed gold deposit. The Hemlo gold deposit is in the Superior Province, in Wawa sub-province, and this unusual Archean gold deposit discovered in 1981, notable for its very high gold endowment, more than 80 tons, and a typical mineralogy compared to typical greenstone gold veins. The Hemlo include molybdenite, telluride, stibnite, barite. Hemlo ore is hosted in a package of highly altered foliated metasedimentary and metavolcanic rocks sandwiched between two granitoid platoons, the Gowan Lake Platoon into the north and Cedar Lake Platoon and Heron Bay Platoon to the south. And the deposit has been described as disseminated replacement zone within a shear structure, the Hemlo shear zone, strongly overprinted by amphibolite facies metamorphism. Talking about its source, the origin of this gold deposit is, as far as I'm concerned, is not typical. There is evidence that mineralization was in place before peak metamorphism and then was subsequently revoked by metamorphic processes. One hypothesis is that Hemlo started as a hydrothermal alteration system in a sub-sea floor or volcanic setting. Another hypothesis is that it's a synmagmatic intrusion-related system. The nearby Cedar or Lake Plutone could have contributed fluids. Regardless of the initial source, by the time of major metamorphic event, which is about 6 to 7 kilobar, about 600, 650 degrees C, the ore assemblages existed as fine-grained disseminations of pyrite, arsenopyrite, stibnite, sulfides in the rocks. And during this metamorphism, new fluids were produced by devolatilization and partial melting of the ore-bearing rocks themselves. Tompkins and colleagues 2004 showed that minerals like arsenopyrite and stibnite in the Hemlo ore began to partially melt at amphibolite facious condition. And this generated gold, stibnite, arsenic, lead, tellurium, sulfur melt, reaching sulfur salts. I can say in essence, the source of gold became the pre-existing mineralization itself, remobilized by metamorphic melting. And this is a special case where the source is local. The rock hosting disseminated gold was effectively reliquefied to liberate gold again. Some external metamorphic fluids likely also flowed through some introducing additional silica. But the key gold-bearing fluid melts came from the breakdown of the early ore mineral during metamorphism. This figure shows how the key ore mineral at Hemlo behaves during metamorphism. So on the x-axis we have temperature, and y-axis actually is the log of sulfur fugacity, or FS2, which is the measure of sulfur availability in the system. The shaded area is a stability field for different sulfide minerals, including arsenopyrite, pyrite, and some others, such as orpiment or realgar. We have the stability field of arsenopyrite, but what's important is what happened as the system heats up during metamorphism around 600, 650. So the peak metamorphism condition at Hemlo is at this temperature. And the system crosses into the liquid field. This means that arsenopyrite is no longer stable and begins to melt. So these are the reactions shown here. Reaction 1 and 2 shows that how arsenopyrite breaks down into molten arsenic and sulfur liquid, especially when FS2 is high, as expected in Hemlo. And this melt can incorporate not just arsenic and sulfur, but also stibnite, tellurium, and most critically, gold. So this diagram provides strong thermodynamic evidence that gold was remobilized in situ from pre-existing ore minerals during metamorphism. In other words, the original gold-bearing sulfide at Hemlo effectively melted and reliquefied, turning the rock itself into a new fluid source. Talking about the transport, in this diagram here, we can see pre-mobilization. Pre-mobilization. It actually is the highest strain accumulation is happening here, and we have transport at Hemlo that's really unconventional. Instead of gold-bearing fluids sending from deep structures, movement occurred locally within the deposit. During peak metamorphism, the ore assemblages partially melted into stibnite and arsenic-rich sulfur salt melt. And this melting coincided with intense ductile deformation. And as the rocks experienced shearing, high strain compressional zones developed where the melt began to segregate from the surrounding foliated host rocks. What's happening here in B, we have melt mobilization and some local transport. The molten gold-bearing phases was then squeezed out of high strain zones and migrated short distances into the low strain extensional structures, often only maybe centimeters to meters wide, and these are can be local conduits and traps. And these movements under ductile conditions resulted in high-grade enrichment of gold, where the melt pooled and crystallized. So then we have post-metamorphic remobilization. As the system cooled around 300 degrees C, residual fluids or melts continue to mobilize minor amount of gold, and these were likely focused into later stage fractures along the Hemlo shear zone. And although the transport distance remained short, this post-metamorphic remobilization added complexity to the final distribution of gold, overprinting the earlier high-temperature features with the secondary generation of gold-bearing quartz veinlets. So Hemlo's main stage transport was, as far as I'm concerned, is unconventional. Instead of a long distance sent of fluids from far below the critical movement was on small scale within the deposit, driven by deformation. As the ore assemblages melted into stibnite arsenic-rich molten phase, the concurrent tectonic deformation and shearing caused these melt to segregate and migrate from high strain compressional parts of the rock into low strain extensional parts. Essentially, the gold-bearing melt and associated fluids were squeezed out of tight foliated zones and injected into nearby dilational sites, such as boudin necks, fold hinges, and extensional fractures. And these dilational zones were on the scale of centimeter to meters. Small quartz-filled fractures or schistose zones that opens during metamorphism. The transport distance could be meters to tens of meters, not far compared to most hydrothermal deposits. However, this segregation greatly improved the grade in the dilational zone by concentrating gold. Some fluids may have escaped upward along the Hemlo shear zone during metamorphism, but much of the gold was likely redistributed locally. And this process is akin to AQS and melt mobilization under ductile condition, quite different from typical open fracture flow of cooler fluids. After metamorphism, as the rocks cooled to about 300 degrees C, some residual melt or fluids continue to mobilize minor gold, leading to small scale remobilization along the late fractures. In overall, Hemlo is a case where metamorphic transformation of an existing disseminated system led to a second stage concentration of gold. It underscores that traps in gold deposits can be reactivated or enhanced by later events. STT in Hemlo spans two stages, initially likely hydrothermal source and trap, and later a metamorphic reworking where transport and trap were governed by melt segregation in a shear zone. The end result was an ore body with highly unusual mineralogy and extremely high gold enrichment in zones that were effectively self-trapped by the rock's rheology. So Hemlo's story is a testament to the versatility of the STT concept. Even when the trap is not a cold site intercepting the fluids, but a dynamic partitioning during metamorphism, the same principles of focusing and deposition applies.